Hey guys, welcome. Yeah, so when you're first learning about complex integration, you should start with this video. And that's because in this video, we define some really important terminology that we're going to use over and over in videos to follow. And we're going to get our feet wet on what we mean by complex integration. Now, this video is broken into two unequal halves. So let's begin the first half with this, which is a complex valued function f of a real variable t on a fixed interval like this would look like the following, which is f of t is equal to u of t plus I times v of t. And since u and v here are functions of the real variable t, we say that u and v are real valued. And f here is integrable if u and v are integrable. And in that case, we'd say that the integral from a to b of f of t dt is equal to the integral of its real part plus I times the integral of its imaginary part. Yeah? Okay. And of course, all other differentiability rules apply. For example, the fundamental theorem of calculus. With this, let's go to the second half of this video that's got a lot more. So, this is a subtitle for the second half, which is complex integration on a curve in the complex plane. So, using parametrization, we can represent a curve in the complex plane as z of t is equal to x of t plus I times y of t on the interval a to b for t. Yeah? Okay, and so this is what we're doing. So we take the real segment from a to b and map every point, including a and b, using z to form a connected complex curve. Yeah? Okay. So by complex curve, I mean a curve in the complex plane. Okay. And the curve is set to be continuous and differentiable if x of t and y of t are continuous and differentiable. A curve or an arc C, and we use the letter C to represent a curve quite a lot, and we use C to also represent a contour, which we'll define in a little bit. But yeah, a curve or an arc C is set to be simple, or a Jordan arc, or a Jordan curve if it's a curve, if it does not intersect itself. And of course, doesn't intersect itself means that if T1 is not equal to T2 for T1, T2, and AB, then Z of T1 is not allowed to equal Z of T2. But we do allow Z of A to equal Z of B. That is, we allow for starting and endpoints to meet, in which case we'd have a closed curve. First, some visuals that are going to help you. So this arc here is simple, but clearly not closed. Yeah? And so we call it a Jordan arc. And this here is a simple and closed curve. Okay, and no real importance attached to arc versus curve. I could have called this a curve, right? But important whether it's simple or not, and whether it's closed or not. And we'll have visuals for not simple and not closed, right? Obviously, you see not closed actually. So we'll have a couple of visuals on not simple in a second. But first, a more important terminology. As I've already said, Z of B is allowed to equal Z of A. And in that case, we say that C is a simple closed curve, right? Like this. You already saw a visual. And now on to direction, right? Which is on a closed curve, the counterclockwise direction is considered positive. As you see this arrow, we do complex integration counterclockwise so as to make the integral positive. If you go clockwise, then the integral is going to be the negative of what you'd get if you went counterclockwise. So it's equivalent to like the integral from a to b versus b to a. Yeah? And now the promised visual on not simple and not closed. And the figure 8 is not simple but closed. Yeah? Okay. And more terminology. So a complex integral on a closed curve is done in the positive direction. As I said, positive direction means counterclockwise. I've already said that, but just spelling out the convention that we go counterclockwise, meaning positive. Yeah? Okay. And we say that f is piecewise continuous if the interval from a to b can be partitioned, and f is continuous on those partitions of the interval from a to b. Yeah? And that's what I say here in this slide. And just giving you other wording. And a smooth arc C is one for which z prime of t is continuous. Now, let me help you understand this. So, smooth is an actual math word, right? Like, it means continuous and differentiable, right? Now, if we think to real variables, real variable calculus, that is, consider the function f of x is equal to the absolute value of x. That's an example of a function that is everywhere continuous, but not everywhere differentiable. In particular, since the absolute value of x has a v as its shape, at that vertex of the v, we have what's called a cusp or a sharp turning point, and that's why it's not smooth, right? And that's to say that, like, if you take the derivative of the absolute value of x, the derivative will have a graph that has a jump discontinuity. And so here, that requirement that the derivative be continuous will make the function smooth. And in this case, it will make the arc smooth. And now a very, very important word, contour. So a contour is an arc consisting of a finite number of connected smooth arcs. And so we do complex integrals frequently on contours. And in fact, a lot of other people call complex integration contour integration because, as I said, complex integration is done frequently on contours. The contour integral of a piecewise continuous function on a smooth contour C is defined to be the integral over the contour C of f of z dz equaling the integral from a to b of f of z of t times z prime of t dt. Now, I use this equation to do a couple of complex integrals, and so I'll link those videos below this video so that you can see it in action. But to understand this equation a little bit better, remember, we took the real segment from A to B to form our contour by mapping the real segment from A to B using Z. And therefore, it makes sense how C turns into A to B. Now, to understand the difference between this integrand and this, recall again our parametrization and the fact that Z equals x of t plus I times y of t. And therefore, dz is going to equal x prime of t plus I times y prime of t all times dt. And let me display that, right? Okay, and finalement, when doing a contour integral, the value of the integral is independent of the parametrization. And this last fact I prove in a video I made a while back. And so I'll link that video below this, but soon enough, I'll offer another perspective of why this very last fact is true. So I'm going to, by the time I make this other video, I'm going to offer you two different ways to realize why the parametrization does not have any impact on the value of the integral. Yeah? All right, cool. All right. I hope you enjoyed this and lots more videos to come on complex integration, and keep watching. Take care.